The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome everybody to our webinar today. Just to inform you, everybody is muted and will be muted. So please, if you have any questions, then just type them in the question box below. And if it's small questions, we will answer them during the webinar. And if it's bigger questions, Daniel and Frank are going to answer them at the end of the webinar. The title today is Quality Assurance in Terrestrial Laser Scanning Networks Beyond the Crystal Ball. And the presenter today is Daniel Bujans. And with him today is Frank Gielsdorf. We will have the same presentation in German. Daniel and Frank are both working for TechNet, and they are both working on the software SCANTRA, which is a registration software. And just to give you some numbers, some of their customers are registering thousands of scan positions in that software and are having less to no trouble if they are using it correctly. And with that said, the stage is yours, Daniel.
Thank you very much, Martin, for the kind introduction. And also thank you very much to PointCap and Laser Scanning Europe for the invitation. So before we're going to start and having a look at where I'm talking about registration in general, I should mention I'm actually going to start and pick up where Richard and Martin have. I think they had a webinar 2 weeks ago. So we're going to focus on everything that comes after registration. Before we're going to start, I'd just like to introduce my laser scanning life in 10 seconds. When I was in 2003, I actually studied geoinformatics and surveying, and I was given a magic box, and that was a Cyrix 2500 scanner, and that was my initial contact, and I'm not doing everything other, since then. In 2009 and 10, I actually moved to Australia to work for a very interesting company called Scanalise, and that was a company who did deformation measurement or wear measurement on crushers and mills, and I was a specialist for registration and quality assurance. It was a very nice job, and yet I quit because I made a list of problems that I couldn't solve. And so I then went from 2010 until 2018, I moved to TU Berlin in Germany, and it took me about 6 to 7 years to get rid of that list. And as you can see, there's a quite detailed list. All of them are related to quality and calibration and the like, everything that deals with the quality of the point cloud and the scanner itself. From 2016 to 2018, I actually performed a research project with TechNet, and I actually joined the SCANTRA team in 2018. So some of the examples that you may hear in this, that you will see during this webinar, will be part or are part of the Taming Error series that you will find in the laser scanning forum, and also I post them frequently on LinkedIn. So if you want to have a detailed read through this, you will find the first 7 parts on LinkedIn. So in this webinar, we'll talk at the very beginning. I will talk about the impact of registration itself. I will, in terms of which tools have been used, I will use all different registration strategies or were used: targets, cloud to cloud, plane to plane, or a combination thereof. And for quality assurance, I will use the latest release, SCANTRA 2.4. And in terms of data, the data sets come from, I'm not going to particularly mention which scanner was used, because sometimes people will think that it's the scanner that's bad. I don't want trying to post that image. So Faro XNS series scanners we used, like a BLK, RTC, and also ZNF Imager 5010 and 5016s. The data sets that I've used here in this webinar stem from our support or consulting clients. And now it was really interesting. The question was, which examples should I choose? And what I did was I actually had a look at the laser scanning forum and just picked somewhere, where I thought this is a subject that comes up more frequently. So for instance, you can see on the right-hand side, 664 matches for registration error. Trust my survey, a point cloud, out of calibration. These are questions that come up here and there. And yes, so these are actually the subjects that we're going to deal with. So why is registration so important, or why is it so dangerous in general? So you can see this is actually the project plan or the processing chain of the laser scanning project. So traditionally, or hopefully, you've performed some planning before. Then you start data acquisition. Then you start primary data processing. That includes three steps traditionally. That's data flow, where you eventually have to convert your scans into a particular format. Maybe you perform some filtering, and if your scan project, has more than one scans, then you have to perform registration. And then the secondary data processing actually usually contains the step where you generate deliverables for your client, where you actually add value to all these points. And now you can see actually that the registration is quite dangerous because it has a systematic impact onto all deliverables. So in other words, if your registration is wrong, your deformation measurement will be wrong, your construction site monitoring will be wrong, and that's actually what you're trying to avoid. Another problem is, and of course, errors occur, but you should find them before you pass them on to another processing step, because otherwise you end up in a vicious cycle between passing on something to secondary data processing, receive it back because the draftmen are not happy, and so on and so forth. And because that would be quite costly, and that should be avoided at all given costs. So this is actually a post in the laser scanning firm. I think it was from last week, and you see the status quo 2020. So how do people perform quality assurance in laser scanning projects? And just highlighted three particular parts of this post, and it says visuals, seeing, and see. So in other words, people tend to look a lot. So that means, when you look at engineering projects in general, it is absolutely normal to perform a visual plausibility check, and it's also recommended. But what is not normal and not recommended is to solely perform visual quality assurance. And the argument that speaks for this is quite plain and clear. There's way too much information. There are way too many points. There are limitations in perspectives. And of course, you may be able to find, large outliers, but the small, subtle deviations are usually not visible. So as soon as they accumulate, you will end up in a large area that you may find, but you do not find the source of all evil. And this is what makes it so tricky. So the basic information that you need in order to be able to find errors is called redundancy. And we have redundancy in all different fields of engineering. So for instance, parachutes have a safety parachute. So if one fails, the other one will save your life. You have it in braking systems. So for instance, in aeroplanes, if one fails, the other one steps in and helps you to save the day. And so if we try to interpret or simply just try to interpret redundancy, then it means to have more or do more than actually required. So let's go to laser scanning. So you can see, first of all, there's a small picture of a scanning network that I will use the same notation throughout the talk. So whenever you see a circle, that's actually highlighting the location of a laser scan. Whenever you see an arrow, it means this is a registration between two scans. So this is roughly what we're going to talk about. So networks and how they can be designed. So let's get back to redundancy. So when we talk about terrestrial laser scanning projects, there are different sources how you can introduce redundancy. So for instance, you can have contra points based on GNSS, tachymetric, and/or leveling network measurements. You can add additional registrations, regardless which strategy was used. Again, please have a look to Martin's and Richard's talk 1 or 2 weeks ago, or inclinometer data. So all these pieces of information contribute to the overall redundancy in the network. So, and now, first of all, it's very important to understand if there's no redundancy, it's impossible to find false registrations. It's just like the example that I showed you of the parachute. If you just have a normal parachute without a safety parachute, if your one and only parachute will fail, you will just, it's going to be ugly, and that's something you should avoid in engineering at all given costs. So if we just take this very small example and then introduce some redundancy, then it's going to look like this. So I'm adding some crosslinks in between. different scans so that I receive a self-controlling environment or network configuration. And the cheapest option to introduce redundancy is to actually add more registrations if possible. So whenever you're in the field and you see the option, the chance to have some crosslinks, some loop closures, I highly recommend to do this, because you could, of course, try to be quicker in the field, but once an error occurs, you will waste a lot more time in the office trying to find that error. So this is a data set that Martin and Richard actually showed 2 weeks ago. So this is what I'm referring to this as the point cap data set. We have 78 scans. It's a residential building, roughly 100 square meters of ground area, and spans over 3 levels. And so they actually processed it by using artificial targets they brought into the scene. They had 457 target locations, about 1,500 correspondences. This is how they processed it. I just took a different approach, so I actually followed SCANTRA's plane-to-plane solution, so I didn't use any targets at all. This is what you see here on the right-hand side is an intensity image of one of the scans, and everything that's tinted in some color actually highlights the location of a plane. So if you see bluish colors, then it actually means that a plane is facing upwards or looking downwards. Red is roughly in X direction, green is in Y direction. And another important thing to mention is that every single plane has got different characteristics, so we don't treat them all as being equally precise. So we actually weigh them during registration, but that's another subject altogether. So per scan, we actually detected 1,200 planes, and in total we used about 97,000 natural planes for this project. So then we have a look at what you can actually do with the data. So the very first configuration that you could choose is the following. So again, we have 78 scans, and if you connect them by 77 registrations, as you see on the right-hand side, all of them are actually connected to each other. But there's actually no control. There's no redundancy that allows us to check if there's erroneous registration somewhere in this configuration. And that's, of course, very dangerous, as I mentioned earlier on. So what we can do is we can also add some more connections. So this is the configuration that I personally chose. So I have 145 pairwise registrations, and I also included the inclinometer as an additional configuration that, of course, checks only 2 degrees of freedom, namely the rotation about the X and Y axis. So now let's talk about quality. You see, in every software, you usually have red, green, or blue somewhere. Now, it's very important to understand is when you see that in SCANTRA, red, green, or blue, that doesn't mean that the registration is correct. It just highlights the quality of the registration. So quality means you see there at the bottom at this small box, highlighted by the red box, you can see sigma T and sigma phi. If you happen to be a surveyor, then you know that sigma highlights a so-called standard deviation, which is a quality measure that we use in this field of science. And it actually means, so sigma T means that a translation is shaking by, in this case, by 0.3 millimeters, and is rotating. And let's say that the sigma phi actually highlights the rotation. So, and that can be considered as some kind of a shaking, some kind of haziness of the measurement. But again, it's very important to understand. It doesn't mean that these registrations are correct. When you see a green line in SCANTRA, it actually means that the sigma T, which highlights the translational quality, is below a millimeter. If it's yellow, it's between 1 and 3 mil, and if it's red, it's actually larger than 3 millimeters. The quality of these measures actually depends, of course, on the applied scanner, but actually a lot more influence is brought into this game based on the configuration and the characteristics of the overlapping region. So again, if you can have 100% overlap between scans, but it also depends what is what's the content of the overlapping region. If you're somewhere standing on a parking lot, you have a lot of information in vertical direction, which means the vertical component is very stable, but you may not have something in positional direction. So you always want to have sufficient geometric content. So that means, or contrast, if you so wish. So that means we have information that looks in 3 cardinal directions. That's roughly what definitely helps to receive good registration parameters. So let's talk about quality. So you can think of every block adjustment, which is actually the quality assurance component that you should use, as some kind of a trial. So you have some suspects, you have defendants, and in this case, this is the American system, you may have a jury. So, and the problem is actually that all different defendants say something different. The control points, geodetic north is facing that way. The inclinometer says, the gravity center of the Earth is in that direction. And the registration says something contradictory. And this is actually the challenge, because every observation, every source, every single observation can be erroneous. And that actually means that contradictions are inevitable. And I know that, registration is always treated by some, companies as being a triviality, but it's actually not. It's actually, engineering at its finest. And therefore you need, of course, in engineering, we are numbers people. Staring won't help. And I will show you some numbers that you can use for this task. So what can you actually throw into the block adjustment? First of all, you can see these are different types of information that you can feed into the block adjustment. So for instance, cloud-to-cloud registrations, plane-based registrations, inclinometer, local or global targets. It doesn't matter at all. So, and you can think of the block adjustment as some kind of big ball of wisdom where, where it is actually checked if which of the information that you fed into this block adjustment is correct or not. So the question is, how do you know? So in general, the task of the block adjustment, of course, is to minimize tensions within your network and, of course, to identify outliers. What that is, I will tell you later. Then in addition, it also performs an error propagation. I will also explain that to you at the very end of this webinar. So at the end, what you're going to get is error-free and adjusted registration parameters. This is the task for the block adjustment, and of course for the whole processing chain in the light of quality assurance. So now I'm going to show you the outcome of the block adjustment based on the plane-based registration. The mean misclosures are 0.39 millimeters, the median is 0.3 millimeters, and the maximum misclosure is 1.9 millimeters. And now I'm pretty sure that a lot of you may say, excuse my French, bullshit, I've heard that before. So, and this is actually another part of a post from last week who said, you can never trust the results with any registration software. And when I read this, I was actually kind of furious, but then also it reminded me why I actually quit my really nice job in Australia, because I was in the very same position. And that was actually now the motivation to give this webinar, to show you numbers that are reliable and that are really, that are sound and meaningful. So let's have a look at how this may work. So now I'm going to show you different ways of how to measure height differences. This is the most simple form of surveying. So usually you learn this in the very first semesters. So, and probably you, if you've done this, you've experienced how to work with a level, which is so-called geometric approach. What you can also do is you can use a trigonometric approach to measure height differences. And if you're on a very extraordinarily tight budget, you can also use a stack of pancakes, a piece of wood, and a tennis ball to check if the stacks of pancakes are leveled. Now that may sound odd, but the point is, all of these 3 approaches that I just shown here measure height differences. Yeah. Some more precise, some don't. Yeah. But now let's get to the crucial point. All observations can be assessed in one column block adjustment because they all just yield in height differences. Yeah. And that's the whole point of the quality assurance approach. So how can we do this? So also what you probably learn in survey class at the very early start is to perform a leveling loop or closed leveling network. So the general idea is that you have a starting point and an end point that are identical. Yeah? So that means you do all your leveling. So you can see, for instance, that in this example, you level up the mountain, down the mountain, and then if you're in the very same position as before, then hopefully, or in theory, the sum of height differences should be equal to 0. Typically, of course, this is not the case. So there are 2 different cases that we have. So, for instance, if the misclosure is roughly in the range of the assumed precision, then everything's fine because that's what we expected. But if the misclosure that you receive is notably larger than the assumed precision, then you can be pretty sure that your data contains outliers. So how can we use this approach to laser scanning? So first of all registration strategies that Martin and Richard talked about yield in registration parameters. So the question is, why do they all use different quality measures? And why do we need different algorithms to compute their quality measures? And so what actually we did in SCANTRA was following the very same principle that I showed you earlier. We use constraints in the form that we concatenate registrations. So for instance, let's say we have 3 scans that are connected by 3 registrations so that they form a triangle. And if we then have a look at all these different registration parameters, we should yield in a zero transformation. So that means is the equivalent to having sum of height differences should be 0. That's the very same general idea behind this. The beauty of this approach is that, of course, if you do leveling, if you adjust a leveling network, you just have 1 degree of freedom, which is height differences. Registrations have got 6 degrees of freedom. We have 3 translations, so you can shift your scans in 3 different directions, and also you can rotate about every single axis. So that means the procedure by using these constraints actually controls every single degree of freedom. So if there's a misrotation about one axis, you can tell as soon as you check the sum of registrations. And that's actually the power of this whole approach. And of course, it's the other beauty of that is that you can perform quality assurance of scanning networks regardless which registration strategy was used. Of course, the other practical question is how do you get it into the software, but that's again another subject. So, and now we get to the question, the big question in quality assurance: is everything in perfect order or not? So, can I pass on my registration, my registered point cloud to the draftsman, or do I need to do something? So, I now picked one particular registration, and you can see here VT on the right-hand side, highlighted by a red box, says I have a residual or misclosure of 0.3 millimeters. So, and now the question is, what is an outlier? When do I need to do something? So is 0.3 an outlier? Or let's assume that VT would be 3 millimeters. Is that good or bad? Or is it if it's 30 millimeters? Yeah. So let's have a look at and try to define what's an outlier. So in this example, I actually, we have a chassis of a car, and we have 3 different measurement devices. And the task is now to measure the length of this chassis 10 times. And then we use these 10 observations or measurements and then compute the standard deviation. First low budget tool that we use is a tape measure made of paper from a well-known Swedish furniture store, whose accuracy is assumed to be 2 millimeters. The second device is also from Sweden. That's actually depicted here, a company that some of you may know is a geometer total station. The accuracy of that is probably 1 millimeter. And then the high end of the spectrum, the peak of evolution among these 3 different devices is actually a laser tracker with an accuracy of 5 micrometers. So let's have a look at the results. So we measured 10 times with a tape measure, compute the standard deviation. The result is 1 millimeter. We did the very same with the total station. The result is 1 millimeter. And you probably guessed right, we did it again with the laser tracker. The result is 1 millimeter. Now let's raise the question, what's a good outcome and what's a bad one? So now I'd like to introduce a concept that probably, because in laser scanning, there are a lot of people who are non-surveyors. So I'd like to use a concept that is widely known across all engineering fields, which is signal to noise ratio. So if we now translate the signal to noise ratio into the terms of surveying, then we can say it's the ratio between a residual and its assumed accuracy. So if we do that for the very first result that we had, which was generated by the paper tape measure, we had a ratio between 1 millimeter, which was the standard deviation of ranges, divided by 2, because that was the quality that we assumed. And the ratio is 0.5. So that means actually, if we just try to conclude, that's actually a triumph, because we were actually twice as good as expected. If we now look at the result from the laser tracker, then we can see it actually is not very spectacular, actually, and that's a good way. That's actually something good if that happens in surveying, because it actually confirms our expected accuracy, and that's quite important later on to understand. And now, if we look at the result by the laser tracker, it shows 1 millimeter divided by 5 micrometer. The ratio is 200. So we've done 200 times worse than expected. So in this case, we can clearly say it's a catastrophe, but it also tells us something very valuable, because we know that there was an outlier, something went wrong, and we have to do something about it. Yeah? So it is actually good information to know this, and this information is quite important to assess how well we've done. And in probably some of you remember, adjustment, or if not, if you haven't ever heard adjustment theory, you probably had statistics. And there's a very basic rule, which is called this 3 sigma rule, where you say if the signal to noise ratio, or we call in geodesy we call it the normalized residual, is larger than 3, then the observation is most probably an outlier. The larger this value is, the more likely it is to be a real outlier, and we need to do something about it. So let's have a look at this one particular observation that I showed you earlier. So the question was, what's an outlier? 0.3, 3 millimeters, or 30 millimeters. So in this case, 0.3 millimeters is not an outlier, because you can see there the green box at the very bottom, S nil, is the normalized residual, or our interpretation of the signal to noise ratio is 1.6. Everything is in perfect order for this particular observation. So again, but this, I show you now the concept for registrations, but the beauty of that approach is that you can use it for all sorts of different registration types. So you can feed point to point, cloud to cloud, cylinder to cylinder, or some futuristic approach that will come out in 5 years. As long as they yield in registration parameters, you can use the very same metrics to these approaches. But you can also use it to global or local correspondences, so from artificial targets, for instance, or to inclinometer readings. So, and again, for instance, at the bottom, I just have another example. So you can see the outcome of the block adjustment is shown on the right-hand side. So VT, that's the misclosure between registrations. So we have a VT or residual misclosure of 2.4 millimeters, and you can see in the center, this is the assumed accuracy or noise, if you so wish, and the signal to noise ratio is 23 times higher than expected. So we know this is an outlier, and we have to do something about it to ease the tension within a network. And of course, we don't want to give erroneous stuff to our colleagues or draftsmen. Of course, 2.4 millimeters, you could probably argue that's not too harsh, because it's probably within the noise range of the scanner. But again, if you have 10 times residuals of this size, you may end up in larger misclosures. So I personally would do something about it. So how is it realized in SCANTRA? We have in SCANTRA some kind of a to-do list, which is called the inspector window. So this list shows you all observations that are where the normalized residual is larger than the ratio of 3. So you can see on the right-hand side in the green box, you can see these are, of course, they have to be larger than 3. That's the first thing you see. If you look two columns to the left, you see V. That's again the residual. But if you look to the very left-hand side, you can see that, of course, what I talked about earlier, they can use the very same approach, the very same metrics to identify outliers that come from different observation types. So be it vertical axis, which is, for instance, in the inclinometer reading, transformation that actually highlights registrations of all sort, or there could be point correspondences, for instance, between local targets or global ones. So 2 words of advice: the higher your redundancy, the more precise you can actually pinpoint where an error occurred. Yeah? So for instance, if you perform a measurement around your hometown and it requires 1,000 scans that are all registered in a big loop by 1,000 registrations, as soon as you close the loop and you have a big outlier, you know something went wrong on this on the way, but you don't know where. Yeah? So that means if you then increase your redundancy, you will be able to tell where the error occurred, but we will have a look at this later on. The second very important piece of information is the higher your accuracy, the smaller the discrepancies can be that can be detected. It's again, if the question is, as I showed earlier with the example of a chassis, if you should detect, let's say, the thickness of varnish on this car, and you use this tape measure made of paper, you will not be able to do this. Therefore, you need the accuracy, for instance, of the laser tracker. So that brings me to the very first practical example, and this is actually, again, as I told you earlier, taken from the laser scanning forum, and there was one question: wrong registrations or wrong control points. First of all, some remarks, and this is quite interesting. Of course, I'm not trying to bash total stations. Well, first of all, I'm a surveyor. This is my tool, but nevertheless, it's very important to point out that total stations are not made in heaven. Just as every sensor on the market, they all have, of course, errors. And in the case of tachymetric observations, of course, the network configuration has an impact onto the outcome. They're all subject to error accumulation, and of course, but we could compute this using error propagation. And there are other errors that are just involved in the measurement process. For instance, if you try to survey targets, then of course, if you survey one of these checkerboard targets, you have to switch into the reflectorless mode. If you survey a prism, you switch modes, and they have different accuracies. And also there are other components that people very likely tend to forget, because you also have the digitization error of the checkerboard targets, for instance. There is not the point in the point cloud. Yeah? So you typically, for this kind of target, you use image-based correlation approaches. They keep looking for this pattern, and then in the end, usually you get a correlation efficient. So, and the problem with that is, I mean, these approaches work great, but the quality measures are very hard to interpret. So, for instance, you could receive, let's say, a correlation coefficient of 73%, but if you have a look at the result, let's say the center of the target is somewhere entirely different, or vice versa. You know, the numbers are great, you know, and the target looks good. So, long story short, survey targets are not error-free, and as some people claim them to be. So, let's have a look at the first example. Again, these are practical cases by some of our clients. This is a tunneling system underneath the factory, which is roughly aligned in a grid. I just show a very small part of it. About 400 stations, not too big, 100 control points, which have been observed by total station measurements. And the registration was performed in a combination between targets, you know, global targets in a superior coordinate frame, but then also planes and local targets between individual scans. The problem here, you can see it roughly. You can see these black dots. These are individual scans, and you can see the tunneling system. So you have not much geometric information to solve the longitudinal degree of freedom. So in other words, you have floor and ceiling, which helps you to fix the vertical component and the rotation about two x and y axis. You have the walls on the two sides, but you have not much in direction of these tunnels, and this is why this client has introduced you know, targets to support plane-based registration. So this is roughly how it looks like. You can see this is just a detail again. You can see the large circles are you know, scans or scan positions. The small circles are local targets. The dashed line between the circles are, you know, just correspondences, and then you can see the triangles. These are global control points. So now let's have a look at the actual part why the client has called. He said, look, I have a small chunk of the projects, 88 stations, not really much. I have 34 control points and I have 88 correspondences. And when I run the block adjustment, I get pretty large residuals. You can see here residuals of up to 10 meters. And the biggest issue was he sees residuals between superior coordinates, between local coordinates, and between registrations. So again, he couldn't really pinpoint where the error was coming from. So then I actually took this data set, and the very first step that I did, I switched off all point correspondences, just had a look at the correspondences, and I increased the local redundancy. So you again can see here that this is just a very small part. So again, the circles are laser scan positions, the arrows highlight you know, targets between these registrations between these two stations. And so that was the initial state, and then I just added more registrations. what was interesting to point out of I think in these 88 stations there were only 3 false registrations. So the block adjustment told me now I reached a state where I have no contradictions among registrations, and then I switched on all point correspondences. And now you can see this is again a screenshot from SCANTRA, and if you see something thick lines in SCANTRA, it means not good. Yeah? So the thicker the line, the more significant is the tension in your network. So the problem that was here, and of course these were 2 kilometers of tunneling. The problem is, of course, everything looks the same, and the problem is if one person places targets, well, human beings tend to do stuff in a repetitive fashion, and that was the problem here. That there was some ambiguities between target positions, and that yielded in false point correspondences. Once they were fixed, everything was fine. The misclosures to the control points were below 5 mil, and the scan to scan, the relative accuracy was about 0.3 millimeters. So everything was sorted then. So that's the first example. So here we had actually a mix between 2 different sources. But then I had another very interesting case lately, a bit larger project, 2,500 stations, 4,100 registrations. The client has used cloud to cloud for the outdoors, and for the interior of this example, he used plane to plane. They used about 130 control points, and what was interesting here, once he ran the block adjustment just with registrations, everything lines up perfectly, looks very, very good. But as soon as he ran the block adjustment with his control points, he sees residuals up to a decimeter. And this is the problem. When this occurs, people start to, well, I wouldn't say freak out, but lose confidence quite quickly. And then he asked the question, then he had to look at, are there any wrong registrations in there? But again, his redundancy was great, so we could rule that out. And then we had a deeper look at his control points. So the block adjustment at first showed everything makes perfect sense, but, and here's the point, depending on who you ask, the Earth is either a potato, an ellipsoid, a sphere, but never a flat disk. So in this case, the project area was about 300 by 400 meters, and his control points were in a superior coordinate system. And of course, the Earth has got a curvature, and you need to consider that. So, and plus, he used UTM coordinates, which are subject to scale. So we developed 3 different solutions. First option was we could have scaled, or the client could have scaled the point clouds. Well, of course, this is what people barely do, because then all the measurements in the point cloud wouldn't be metric anymore. So usually we ruled it out pretty quickly. We could scale the registration parameters, or you can see it's underlined, that was the option that we chose. We could scale the control points. So I'm not going too much into detail, but the compensation that you need to apply, we used the equation by Mittermeier, which was a professor at TU Berlin. And I'm not just going to tell you the variables of it. Of course, you need the scaling factor is what you need, and that you need to apply to your control points. You have the Earth radius, and of course, the scaling factor depends on the distance to the central meridian. In this particular case, if you look at a distance of 300 meters, we had a compensation of 9.3 centimeters, which perfectly explains the residuals that the client has seen. So, yeah, we actually applied the scaling factor to the control points, and project was saved. So now we move on to a very unpleasant subject, which I just called it to calibrate or not to calibrate. This is actually very small but very interesting subject or project that another client had. So 135 stations, 259 registrations in clinometers, and they also had technometric control points. It's not really, again, it's not really complex structure. So usually we don't see these a lot. And so, but what he told us, look, I'm running the block adjustment, and I see some tensions. You can see the largest tension here is a centimeter, and there's some in the higher millimeter range. This is, again, if this wouldn't be an engineering survey, well, it's not a beauty, but you probably could live with that. But what he said was interesting. He tried to manually to perform some counteraction. So he tried to do manual pre-alignment, but it always ended up with the very same quality measure. So there was no way he could improve the quality. And then I had a look at the data, yeah, I then actually told him the following. It's actually a tragic practice in terrestrial laser scanning, because most of the scanners that you see are typically calibrated only once per year. Most of the scanners are not really treated too good because, well, of course, they are quite pricey. So they are used, well, of course, to a large extent. And if they're out of the race, they can't, they can't bring in money to the company. So, and the biggest issue that you have is actually the critical component is the axis configuration, because the rangefinder is typically very stable over time, but the axis configuration is subject to thermal and mechanical stresses. Where sometimes there's an uncertain transport, and some people don't treat their equipment too professionally. And in this case, yeah, it was a mixture. What I found out later on, I tried to actually took the whole project and tried to perform block adjustment in different chunks. And then later on, I found out what the client then said. Look, we use two scanners, namely the company ones, which is well maintained, and a rented unit, which was heavily decalibrated. And what you see here at the bottom, this is just visualized here the normalized residual. Again, just a small reminder, this is the signal to noise ratio between the assumed accuracy and what you get after the block adjustment. And if you look at the scans captured by scanner number 2, then you can see that it ranges between, I think between 7 and 18 times, worse than expected. And that actually ruined this client's day. So not very pleasant. But again, if you would have maintained the second scanner, would have checked the calibration, you could have avoided this scenario, which is very unpleasant. So a very short example to finish off this subject. This is an offshore project, 966 scans, plane-based registration, very good redundancy, very good configuration, 1,540 registrations among scans. But what was interesting here, the client said, look, Daniel, can you see something peculiar in my project? That was all he said, and then gave me the data, and I just had a brief look at it. And I'm now showing you just one part of the project. There were, I think, 4 or 5 levels. I only show you one. And what I did was I performed the block adjustment, and I had a look at the normalized residual, and you can see this local cluster, these local occurrence of tensions that I also couldn't release. And then I said to the client, look, I don't really know what's happened here, but I have a suspicion that I actually thought it would be the very same as before. Maybe they've used 2 scanners and one was poorly calibrated. And then the unpleasant reason was it was an offshore project, as I mentioned earlier. And well, a gust of wind actually caught the scanner and blew it over. So there was a harsh mechanical stress onto the scanner's internal geometry that caused these misclosures in here. All right. So let's move to the very last subject of this webinar, namely relative and absolute quality measures. You've probably seen this project before. It's one of the biggest that I know that was registered in SCANTRA. But that's actually not the point. So it was more than 6,000 stations, 11,000 registration, but the actual pinpoint with the crux in this project was the requirement by the client was the accuracy of stationing has to be better within 1 centimeter. Yeah? So namely an absolute quality measure. So let's have a look at this, what this means. You also probably have seen this if you had a look at or follow the Taming Errors series. So I think apart from us, nobody else gives you, or all give you, relative quality measures. So that means they tell you how well 2 scans fit together. Yeah? So the problem with that is that it actually doesn't consider the entire network configuration. It just tells you how well 2 scans fit together, or at least they claim to do this. Again, I showed you the post from the laser scanning forum earlier. But now what the client wanted, and which is something that we do in surveying for more than 200 years, is called, or we apply the mighty tool of error propagation. So that means independence to reference. We compute how the error accumulates. So again, in the picture below, every scan is represented by a single jigsaw puzzle, and the thumb that you can see on the left-hand side represents the reference, and you can see the larger your network, and the larger will of course be the amplitude if you then wiggle the puzzle around this datum. And the wiggling, this is actually absolute accuracy that the client was looking for. And also, this is quite crucial. These are very important numbers if you do deformation measurement and everything. If you, for instance, do, if you work on construction sites and have to do, for instance, construction tolerance checks in general, that's quite crucial. Or if you want to analyze the quality of your network, then these are the numbers that you actually look at, apart from just looking how well two scans fit together. So. And now I call the next slide accuracy and the art of self-deception, because this is what many people do. Residuals tell you something, but not all. So this is also a practical piece from one of our clients. It's just a small part, 67 stations registered with artificial targets highlighted by these small circles. And then what this company did was they reported how many targets they used and the average, which was 2.24 mil. They also had control points. They mentioned, look, we have 16 correspondences, and the accuracy or the average residuals are 3.5 millimeters. And everybody was happy. Now the question is, if we look at this configuration, the question is, what on earth do these numbers tell us for this particular station on the right-hand side of this network? So now, what I actually did, I took this scenario and put it into SCANTRA and performed error propagation and computed these absolute quality measures. So what these numbers actually I will show you in a minute tell you is by how many millimeters do my stations tumble with respect to geodetic datum. So tumbling means, just as the example that I showed you earlier, my geodetic datum, that was the thumb in the slide showed earlier. And my stations were, of course, the jigsaw puzzle. And tumbling is actually the amplitude of how much the station is shaking with respect to the datum. And there are three different strategies that you can choose how to define such a datum. So first of all, it could be a single station, a single laser scan where you say, look, you are now my reference, and all other scans, all my absolute quality measures should be computed with respect to this one. Probably the one that all of you use or probably thought of first would be tachymetric or ground control points in general, or what you can also do, this is the strategy that's been used in deformation measurement, is you define a reference frame. So for instance, you go to a construction site at a particular day, you perform a block adjustment, then say, constrain the inner geometry of my stations, and then once you get back to the construction site, perform another measurement. All other scans are referenced into the very first reference frame. Yeah, that's the general idea behind this. And the beauty of that approach is that you can draw conclusions for every single station in the network, and not just the ones that are connected to ground control points. Yeah. And again, if you would analyze a total station network, you would also use these very same quality measures, relative ones, to see how well two stations fit together, or total station measurements in this case, and how much the error accumulates over my total station measurement network. And by the way, you do the very same in photogrammetry, in laser tracking, in leveling, everywhere. It's funny that people don't do this in laser scanning, but that's another subject. All right. What I haven't told you was where the ground control points are located, and you can see the triangles are solely located on the left-hand side. So again, we had 3.5 millimeters of residuals, but the problem is that relative quality measures don't tell you the impact of location, so they're not powerful enough in that respect. So, and now this is the outcome of error propagation. So you can see the three different colors. Green means that the absolute error is below 3 millimeters. So it's some kind of, just imagine if you set up your station and the center of the local laser scanner's coordinate system is shaking by less than 3 millimeters. If it's yellow, it's between 3 and 10 millimeters, and if it's red, it's larger than 10 millimeters. And what you can clearly see, the further I get away from my ground control points, which are located on the left-hand side, the larger is the accumulated error. So just to answer the question that was mentioned earlier, so in this case, I have an absolute error of 19.2 millimeters, and that again, this number is a lot higher than the reported numbers that I showed you before, which was I think 2.5 and 3.5 millimeters. So again, people love to portray themselves, and it's not very nice because they also tell their clients, who then believe it, and that leads to all sorts of problems once larger errors occur. So how can I achieve better results? How can I improve my network quality? I mentioned earlier that you can always increase, you can add more redundancy, you can add more registrations, you can tie in inclinometer readings, you can tie in more control points or more precise control points. Also what people, again, tend to forget is to check the calibration of their scanner, because, again, if you have a well-maintained scanner, you will have more accurate results. Or you could also replace your current registration with a more accurate one. These are typical approaches how you can achieve your network quality. Let's have a look at another example. This is just, again, a small part from a project from a construction site. This is a corridor which is about 50 meters long. I performed 10 scans, which are just concatenated in a line. You can see here, again, on the very top, this is the equivalent to the jigsaw puzzle example. So the geodetic datum, my thumb is on the left-hand side, and the error is, the largest error is on the right-hand side, where the error has got, enough space to accumulate. And it's the very same, and for the example, based on the registration at the bottom, where you can see it actually starts at 0 for the reference station, and then increases up to 1.6 millimeters. Yeah. So the very first and cheapest option, how to improve network quality. And again, this is the very same approach that you use in total station measurements, laser tracking measurements, and the like. You place the center or the geodetic datum into the center of your network. So here we would actually place the thumb into the center of the puzzle, and then the error can accumulate into or can actually distribute in 2 different directions. So now we actually decrease the maximum absolute error to 0.6 millimeters. Again, these are stochastic values. That means that we are depicting a likelihood of how much a station is tumbling with respect to the reference. But again, the relative quality measures always remain the same, regardless how your measurements or your network is designed and where your reference point is. And the last option, we could introduce more registrations into a control configuration, and that actually decreases. If we assume the very first configuration, that actually decreases the error by roughly 1/3. So very cheap solution. So now, very last slide. So this is one part of this very big project with 6,000 scans. It's the first level. And again, the client said, look, you have to be better than 1 centimeter. And now I'd like to show you the journey from, fulfilling or showing the journey how you can actually fulfill these quality measures. So the very first configuration that I'm showing you here is based on the very stupid configuration. But before I do this, I just want to also mention something that I haven't mentioned before. This is the first level contains about 587 stations, 1,000 registration, and the point is quality assurance is something you should frequently do. You don't want to find errors at the end, you want to find them as early as possible. So whenever I'm writing something in Microsoft Word, I just have the habit to push Control S, which is save the document in its current state. If I'm processing scan in SCANTRA, I hit Control B. B is the block adjustment. So that means every couple of registrations I check, is everything fine, or do I need to do something? Because these are not too many scans, but again, 1,000 registrations can actually give you a headache, finding the error. So you want to find them as early as possible. So again, the block adjustment takes about 6 seconds on our granny computers. We use Dell XPS, just ordinary laptops at work, which they have a quad-core 2.8 gig and 16 gigs of RAM. So it's not a rocket scientist computer in that sense. All right. So back to the subject. So let's talk about these absolute quality measures. So what I told you earlier, the task was the absolute quality measure has to be lower than 1 centimeter. So you can see on the right-hand side, you can see a gray circle, and that's the datum point that we chose there. So you can see around this gray circle, there are a couple of green stations, and it becomes yellow, and the rest is red. So that means that if we look at the top left, which is the station which we're going to now track over the course of the remaining webinar, then we can actually tell that the error accumulates up to 4.89 centimeters. Yeah? So 5 times worse than the client had to deliver. So the first thing that we could do is we can simply place the reference datum into the center, and that actually decreases the error of this particular station down to 3.69. But it's, again, not too great. So I told you you can also add, for instance, inclinometer information. Sorry. So that means I did this, and then that actually the very same configuration. So the datum was in the center, but just adding this small, component decreased the error by nearly half of it. So we're now down to 1.78 centimeters. And now, of course, you guessed right. We also tied in. Ground contact points based on total station measurements, and that actually leads to 5.8 millimeters for this particular station. And now you can actually see on the right-hand side, this is now the final outcome for this level. You can see the triangles are actually, here's one, for instance. What I should also mention about this client, they are very, very good at being very efficient with their control points. They are very thoughtful where to place these control points, because of course you have to see measuring tachymetric control points also involves labor and hence costs, and they are very effective with this, and I think they're doing pretty well with this. But what is interesting to point out is you can see that here there are a couple of red dots left, or red stations, where the error is larger than 10 millimeters. I think the largest remaining error is about 11 millimeters. But in this case, that was some kind of a room that wasn't really of importance, where they stored furniture. So again, here the client said everything's fine, and yeah, that was the end of it. And here the accuracies for this particular floor, mean residuals and absolute values 3.7 mil for the position. So in 2D, if you so wish, in X and Y direction. Mean in 3D was 5.2, and the residual to the control points 4.1 millimeters. So everything spot on. Client was very happy, and so we were we. And that was it from my side. So I hope it was not too theoretical, and I hope I could tell you hopefully something new. And please don't stare too much at points. And I'm looking forward to your questions if there are any.
Thank you very much, Daniel. This was a lot of information, but it was very interesting from my side. And so far we have one question. If there are more questions, if you have questions, as I said at the beginning, please just drop them in the question box, and then we can answer them. Perhaps I read the first one for you, Daniel, and then Frank can take over. The question is, if we compare TLS versus SLAM-based laser scanner, how can you compare the strategy of your algorithm compared to the SLAM algorithm's philosophy that tries to minimize the drift, the loop closure?
That's actually, first of all, thank you very much for the question, because we're actually working in this field. We just talked about static or terrestrial laser scans. But you can also apply the principle of loop closures to kinematic scans, and we also doing this. I will try to answer this very briefly, but I think I will send the person who asked the question a more detailed question, because actually I have to admit this actually deserves another webinar. But the question is, of course, how can you compare this? The problem is what to compare. We're also working together with some universities who actually had some questions. How can you compare the outcome? And what most people do is they simply just take terrestrial laser scans as a reference, then transform 2 point clouds into the same coordinate system, and then just compute the distance between point clouds. this is how people assess the quality. What we are currently doing is we're developing a strategy of how to use kinematic scans from SLAM-based systems and terrestrial laser scans in a synergetic fashion. So that means we take stable parts from the terrestrial laser scan, for instance, and then stabilize the SLAM-based part. Or what we can also do is, but again, this is under development. There will be more news coming up on this at some stage. Or we can also use the inherent redundancy from SLAM-based scans. For instance, if you walk down a corridor in one direction and come back, you can also use that redundancy to minimize drift. I hope that, again, that was a very brief answer to that question. I will get back to you and then try to also show you some examples. But again, we're currently developing something in that respect. The second question is, I'm just going to read it out. What is your experience regarding the accuracy of the inclinometer of the different manufacturers? Can we trust them? Yes, you can trust them. Actually, it's quite interesting that I've seen, I'm not going to mention any manufacturers, but there has been some developments to the positive side. I mean, before there was one or two manufacturers who had brilliant results and one who stood a bit off. I think now all manufacturers have inclinometers, of course, not of identical quality, but the race has gotten a bit closer. Can we trust them? Yes and no. In terms of the numbers that are being reported, yes. Typically, the manufacturers are a bit, let's say, overcautious. So usually they use a rather pessimistic number in their spec sheets. So when you process them, you could also tighten them a bit up. Can we trust them? I would never. This is an interesting question because I mentioned earlier you cannot trust anyone. You should test and verify all observations. And when we talk about inclinometer measurements, most likely you will see wrong inclinometer readings. For instance, if you work on construction sites where you have heavy vibrations, if you stand on a bridge and a car or a truck is passing by and the building starts to vibrate, if you work close to train tracks or tram tracks, then we see that in SCANTRA that the readings contradict the registrations or other inclinometer readings. That's what I'd like to say on this subject. But again, if more people are interested in this, I can also add more or prepare another example if that's of interest.
Seems like this was all in regards of questions. If you have any other questions which you just are coming up currently, or questions which you get in the next couple of days or weeks, you can just write us an email to support@pointcap-software.com and we can forward it to Daniel so he's able to answer them directly to you. And since it seems like we are completely finished, the hour is over, I will close the webinar now. Thanks again, Daniel, and everybody else. Have a nice evening. Bye.
Likewise.